A practical introduction to polar codes. So in the last and very first part of my tutorial, I was discussing about some very few basics of polar codes, where I was giving a brief overview of what polar codes, what is the context of polar codes, and how to use them in why should one use them, and so on. In this part of the tutorial, we'll dig deeper, a bit deeper into the polar coding system, where we discuss about what do they actually contain. So as I was saying, there are three essential blocks of polar codes. One is called code construction, one is encoding and decoding. In the very first step, we actually would like to decide some parameters, that is called as code construction, which will decide some parameter for encoding or decoding. So what is that parameter? We'll see now. So construction can be explained in a very simple way actually. So it is nothing but selecting k indices out of n indices, that's all. So these n indices are represented by the first n integers including 0, and that n has to be a power of 2, that is one constraint, and the power that is going to be there, that is represented by small n, and this n is precisely the block length, which is constrained to be a power of 2 all the time. So many algorithms exist to do this particular selection. The simplest is what we are going to see, and this is also justified very rigorously in terms of simulations by using this paper. So whatever practical code that you can use in simulations, well, this paper claims that this simplest recursive algorithm can do as good as any complex algorithm that you can use. So in that sense, the discussion of this construction algorithm is sufficient. So the channel that we are going to use for the purposes of illustrating this part of the tutorial is the AWGN channel, and this is going to be used throughout. With modest changes, we can extend this discussion to any other channel, such as binary erasure channel or binary symmetric channel, or things like that. The only parameter that you have to know is, for a given channel, you should know the Bhattacharya parameter of the channel. For those who don't know what is Bhattacharya parameter, they can refer to any standard text on communication systems. This is simply an upper bound of probability of error, which is not very difficult to understand. So and there are very simple formulas available for that. Bhattacharya parameter is something very well known. So what are we going to do in this construction part? So we have to start with some initial, because as I was saying, we are going to use a two-way recursion. So given a single value, we are going to generate two values by using two different functions. So this initial value is something very critical. This is going to depend on the channel condition, the SNR, the channel SNR, so that which is called design SNR at sometimes. So this is going to decide an initial value as by using this function. This initial value is going to be used to generate two values, and these two values can be recursively applied the same formulas to generate four values. So first we started with a single value generated from the initial SNR, and then it generated two values. Those two values generate four values. Those four values will generate 8 values, and so on. We will stop whenever there are n values at the leaf level. We want n values at the leaf level, and then we will simply stop. That will happen precisely after small n levels, because after one level it is 2 power 1, that is two symbols that are available. After two levels, at the leaf level, we have 2 power 2 nodes, and since we have 2 power n number of values that are desired, we will simply stop after small n levels of recursion. Once we stop, all that you have to do is observe those n values, pick the k least values, let those indices be in this set, and output that set. That's all. We have k values. We have been given this n values, and we are selecting k values based on the values that we observe at the leaf level of this computational tree. So only thing that you have to observe is this particular function is nothing special. This is simply the Bhattacharya parameter of the AWGN channel at this SNR, at that SNR. So yeah, that's all. So that's what this below note says. So this is the Bhattacharya parameter of the AWGN channel. If you were using BEC, the Bhattacharya parameter is simply the transition, the erasure probability epsilon. If it is BSE, so epsilon is going to sit here. And then if it is a binary symmetric channel, the initial value is going to be square root of p minus p times 1 minus p, which is the Bhattacharya parameter of the BSE when the transition probability of binary symmetric channel is small p. It is as simple. So this will also sit there in case you are using binary symmetric channel. So it is nothing much of a difficulty. Great. So several things are there that we need to discuss. So the code varies with SNR. So as I was saying, there are many algorithms that are available for code construction. Each construction, when given with different initials, will generate different codes. So what is the best? This question is an interesting question which is answered in this particular paper in the footnote. So that paper essentially says is, I was also hinting at this paper earlier. So this basically says that the choice of a good design is not important, not as much as is very important, and is much more important than the choice of construction algorithm. You can pick any construction algorithm, but choosing a good design SNR much more important than that. Irrespective of the construction algorithm, you can achieve the same performance, but not without choosing a good design SNR. So at different design SNRs, you get different codes which will perform differently, and the best one is something of a choice that you should make based on a very critical observation. So that is what is being explained in there. So all that you have to do is choose a good design SNR that is given in that paper, and then you at that design SNR simply use the recursive algorithm that I have been explaining in the last 2 slides. That's all that you have to do is that, and this is good enough at least up to 64,000 block length. So as I was saying in the very beginning, I have provided several MATLAB modules for your purpose of quick simulations, analysis of polar codes and all. So just go to this link, which is also shortened as this link. This is there in the title slide, so you can as well use this shortened URL, ease.gd by polar codes, or you can download that code base and use it. Once you source that code base, all that you have to do for initializing, basically which includes the construction part of the coding of polar codes, we simply give these parameters which are essential. So this is the SNR that you are going to use for coding, and this is the block length, and this is the message length. Once we give those parameters using this function, the construction algorithm is implicitly called, and the resulting k values are stored, and several other things are also stored. So there is a global structure that is going to be formed as a result of this, and that will pretty much do whatever you wanted. Yeah, so I mean you are set ready for using encoding and decoding blocks, as simple as that. In the next parts of tutorial, we'll be seeing what is encoding, what is decoding in very details. You can actually simulate, write your own codes, different variants, just by reading hopefully the next parts of tutorial are sufficient for doing that. So this is the end of this tutorial, and I'll see you in the next part of the tutorial. Thank you very much.